Hello guys, this is the Mid Dude and today we're doing Physics Unit 2, January 2009. So let's get right to it. So, question number 1. A child's toy is operated by a small motor. The potential difference across the motor is 6 volts and the current in it is 0.2 amps. The energy used by the motor is 120 in 120 seconds. So they've given us 3 quantities, so the potential difference, the current, and time, and they want us to work out the energy. Now the energy you can check in the back of this of the paper as well. They give you formulas. It's E equals IVT. All we have to do is substitute them, so that would be 0.2 times 6 times 120. So that will give us 144 joules. So the answer is C, 144 joules. Question number 2. Which one of the following does not apply to sound waves? Now a brief recap of what sound waves are. They are longitudinal waves, right? They have refractions and compressions. They transmit energy. They are from a result of vibration, result from vibrations, and also they need a medium to travel through. They need a medium to travel through. Now, having said that, let's see which one of these does not apply to sound waves. So they do. So A, they transmit energy. This does apply to sound waves, so we can get rid of that. They travel faster in a vacuum. Now, vacuum means that there are no particles in it. There is no medium for the sound to travel through. So this does not apply to sound waves, and we can move on. But just to double check, let's see C and D. They result from vibrations. Yes, this does apply to sound waves, so we can get rid of C. And they are longitudinal waves. This does apply to sound waves, so we can get rid of D. So the answer is B. Question number 3. 2 coherent sources emit waves of wavelength lambda in phase. At a point where the 2 waves meet, they have a phase difference of 90 degrees or pi over 2 radians. Which of the following could be the path difference at this point? Now, there's something you should remember is 1 lambda, right, follows 1 time period, which follows 2 pi radians. 2 pi radians or 360 degrees. Now, this is the ratio for all these waves, right, in general. Now, they're telling us there is a difference of pi over 2 radians. Now, we need to find out how this pi over 2 radians affects the lambda over here, right? So, how do we get from 2 pi to pi over 2? How do we get from 2 to a half, right? We divide by 4, right? Because 2 over 4 is a half. So, we divide by 4. And then we have to divide lambda by 4 as well. So our path difference should be lambda over 4. Simple as. The answer is lambda over 4, which is D. Moving on, question number 4. The 4 diagrams show waves of different wavelengths approaching slits of different widths. In which diagram will the diffraction be the greatest? Now, there's something you need to remember how we can get maximum diffraction is that it's when slit width, right, the width of the slit equals the wavelength, right? Now for simplicity, I'll put this as W for width and I'll put this for lambda. So we now need to look for the diagram which has the width, right, equals the wavelength. Now you can see for A, that the width is too small. The wavelength is too small. So we can get rid of A, as this is not one of our options, right? We can get rid of A. Now let's look at B. You can see B has the slit width is approximately the same size as our lambda, right? So we can say that over here that this probably is the correct answer. So let's just put this here. W equals lambda. Let's go to C. You can clearly see the slit width is too big, right? It's too big it's much larger than the wavelength, right? Much larger. You can clearly see that the wavelength here is very small. Let me make this a bit easier. See, it's much smaller. Same here, you can see, so C is out of the question. Let's look at D here. You can see that this is still large. W is still larger than lambda. This is still large. It's not the same, right? So we can conclude that for question number 4, the answer should be B, because that's when the wavelength equals the slit width, so we will get maximum diffraction. All right, so question number 5, the heating element for an electric fire is made of a resistance R. It is replaced with a wire of the same material, so that's important, same material, which has the same length but is twice the diameter. So what can we do here? And the question is, the resistance of the second wire is what? Now we know that if it's the same material, it's going to have the same resistivity, right? Same length means same L. So the only thing that's going to change is the area, right? According to the equation, R equals rho L over A, where A is pi r squared or pi d squared over 4 if we use diameter instead of the radius. So let's label this as R1, or let's leave it as R, and our second wire, let's label it as R2, right? Now R2 has the same rho, has the same L, but we know that the area, the diameter is now doubled, right? Now because the diameter is doubled, let's look at the area of the new. So let's say this is the area of R2, right? So it should be pi d squared over 4. So now let's make it 2d squared over 4. So that will be, I'll put it here, so area of R2 should be, let's make it a bit here so you can see, it will be pi times 4d squared over 4. So that should give us, so the 4 will cancel out with one another. You're left with pi d squared. So the area of R2 is pi d squared, right? Now we need to compare this quantity, this area, to the original area of R1 to see the comparison, right? So we can see that this is the area divided by 4. So we can conclude that this should be, so we can say that the difference between this and this is the area is over here, sorry, area of R2 is 4 area of R, yeah, this is 4 times the area of R. Now how do we show it now? How do we show it, right? So let's just put this back here, right? So this would be 4a, right? So R2 is 1 over 4 times rho L over A. Now what do we know about rho L over A? We know that it's the same thing as our original R. So we can substitute that here, and we should end up with R2 is a quarter times R. So that means its resistance of the second wire is a quarter time the resistance of the first wire, which is R. And that's how we have concluded that this is the answer. So the answer over here should be a quarter R. All right. Question number 6. The diagram shows a resistor network. The total resistance between points X and Y is what? Okay, so we should now, because they're in series, we can make this another, we can make it another separate circuit. We can say this instead is 8 ohms, and this is also 8 ohms. Where did I get the 8? I added the 4 and 4 together, and the 4 and 4 together to get 8 ohms, to get 8 ohms, because they're in series and we can add them. All right, now let's look at this. So these are now in parallel, right? Because they're in parallel, what we can do is we can remember it's for parallel, is always 1 over R2 plus 1 over R1 plus 1 over R2, and it goes on according to how many resistors you have. So in this case we only have 2, so this will be 1 over R total 1 over 8 plus 1 over 8. This will be 1 over R total, which is 2 over 8. This simplifies to 1 over 4. So 1 over R total, so the total resistance is 1 over 4. We can cross multiply here, and we will get R total is 4 ohms. So our final answer should be 4 ohms. Now, there's a trick to this. We can skip this, all of this step here. We can skip this part and go straight to the answer only and only if we have identical resistors. And what we can do is we can go straight here and think, okay, so they're identical resistors, there are 2 pathways, so all I have to do is divide the value of the resistance by the number of pathways, number of parallel pathways. So in this case that would be 8 divided by, we have 2 pathways, that'll give us 4 ohms directly. Now this only applies when we have identical resistors. So remember that it only applies when we have identical resistors. So if they're not identical and they have another, so let's suppose we have this, right? We have, let's say, another thing, but this is now 2 ohms. This cannot apply anymore, right? Because we have 2 ohms. Even though we have 2 identical ones, the third is not the same one in its 3 pathways. So we cannot do this method. We can only do it when all of them are identical. So it's very important that you remember that. Okay, question number 7. The speed of sound, so speed is a quantity, the speed of sound is 6,000 meters per second. The wavelength of an ultrasound wave of frequency, so they give us the frequency, is what? They're telling it traveling through a steel girder is what? So they've given us V, F, and they want what lambda is. So we know the equation V equals F lambda. Again, this is in the back of the exam paper booklet. They give you the formulas. So all you have to do is plug it in and first rearrange. So always rearrange first. So that would be lambda equals V over F. So that will be 6,000 divided by 50k. Now 50k is the same thing as saying 50 times 1,000, right? So that is 50,000. That'll be 50,000 hertz. Now what is that? You can put in the calculator, or you can do simply 0, 0, 0, cancel the 3 zeros on the bottom, and you get 6 over 50, which is the same thing as saying 12 over 100. We just times both sides by 2. Both sides by 2 to make it simple, and 12 over 100 is 0.12 meters. So the answer is B, 0.12 meters. Let's move on to question number 8. So we have, which of the following graphs correctly show the relationship between potential difference V and the current I for a filament lamp? Now, I've got this diagram over here. Now this diagram is from the book, from the Pearson Edexcel book, student book 1. And this, they tell us that this is I and this is V, right? This is the current potential difference for a filament lamp, right? But you can see here that the axes have changed in the question. This is V and this is I, and this is V, this is I. So that means if the axes are changing, we're reflecting in this axis over here. So our graph should look like this. Our graph should look like this, right? Let me make it a bit more clear. Nope, go back a bit. Nope. Let me make it a bit more clear. Yeah, we should reflect it over here, and it should look like something like this. So, nope. It should look like this, going upwards like an exponentially increasing graph. So which graph is that? That graph is C. So the answer is C. Now let's look at it from a physics point of view. Now we know that the current, when you increase the current of a filament lamp, right, what happens? We get a higher temperature, right? A higher temperature, what happens when you have a higher temperature? We know that metals heat up at higher temperatures, right? And they have higher resistance. Now we know that R equals V over I, right? So that's basically the gradient, isn't it? That's the gradient of this graph, right? Gradient. So if the resistance is increasing, right? The resistance is increasing, that means the gradient is also increasing. That means that it's going upwards, right? It should go upwards. And the only graph that goes upwards is C. Now why is it increasing? Is because when you give metals current, or an increase in current, I should say, increase in current, what happens to the metal? It heats up, right? So they heat up, and then what happens? The resistance increases. The resistance increases. From that logic, we can say the gradient of this graph is also increasing. That's why the answer is C. All right. So question number 9. We can see that light travels in a semicircular glass block shown below. The ray of light reaches the straight edge of the block at an angle, incidence I, and the critical glass of the angle is C. Which of the following statements is true for the light at the straight edge? So which one are true? So they tell us that when I is bigger than C. So it's basically the relationship between I and C. It's when it's either I is less than C and when I is greater than C. So what happens? So what happens when the incidence angle is less than the critical angle? What happens to the light? We know that some of the light is transmitted, right? And we know some of the light is reflected. Some of the light is reflected. Not all of it, but some of it. Okay. So now let's look at when they're saying when I is smaller than C, right? And what happens when I is greater than C? Then what happens? What happens when incidence angle is greater than the critical angle? Then all of the light is reflected, right? Is reflected. And what about the transmission? Is it transmitted? Nope. Light is not transmitted at all. Light is not transmitted. Light is not transmitted. Now let's see which ones apply to these statements. So A, when I is greater than C, so we're referring to this now, then no light is reflected. That's wrong because we know light is reflected. So A is out. When I is bigger than C, then no light is transmitted. That is correct, right? That is correct. You can see over here that we have done no light is transmitted. So we can conclude that B is the correct answer. Alright, now let's see for C and D. When I is smaller than C, then no light is reflected. That's wrong because we know it's some of the light is. So if this had, so some light is reflected and also some light is transmitted. So for that reason, D is also wrong and C is also wrong. Alright, question number 10. So when a fire engine moves away from an observer, the pitch of the siren heard by the observer decreases. This is because of what? So I've got this diagram which shows the Doppler effect in motion. So there's something you need to remember is that the wavelength of sound waves stays constant, right? The wavelength does not change. The wavelength, you can see over here, the wavelength is the same. You can see the wavelength is still the same. See the wavelength here, here, here. They're still the same wavelength. So A is wrong. The wavelength is constant. The speed of the fire engine increases. Now we can't conclude, we can't say this answer is correct because we can't see. The information given to us does not indicate that the speed of the fire engine is increasing. All we have been told is the pitch of the siren heard by the observer is decreasing. Okay, That's all we've been told. Okay, so now what? Then we go for frequency. The frequency of the siren decreases. No, it doesn't, because you can see that the frequency is still the same. You're still getting the same. You're still getting the same circles. You're still getting the same. You're still getting the same. You're getting the frequency is still the same. Okay, so what's changing? What's actually changing? If the wavelength, we know V equals F lambda, right? And this is the same. And the frequency is the same. Sorry. The speed, we don't know. But the frequency is also the same. So we can also conclude that the velocity is also the same. So we can say that C and B are wrong. See, the only answer we can get by eliminating is D. Now, why is D the answer? Now, if you think about it, the answer is D because the distance traveled by each wavefront increases. Now, if we have a man here, right, and the waves are traveling to him, right? So this is the fire engine going away. Fire engine going away. So this is initially, and it goes, let's say, much farther away over here. I can just copy this. So this is initially, and then it goes further away. So initially, the guy is going to hear lots more sound, right, from the fire engine. But as it goes away, let me put in, it's going to take a long time for the person to hear it. So that means the pitch of it must decrease as it's going away. So that's why D is the answer. Okay, so question number 11. Explain in terms of energy the difference between potential difference and electromotive force. Okay, so we can say the PD, right? PD is what? We can say PD is, or potential difference is, the electrical energy, right? Electrical energy that is transferred between 2 points, right? 2 points, and can be measured in anywhere in the circuit, and can be measured anywhere in the circuit. So that is our first mark, defining what PD is. Now EMF, so we can, EMF is what? This is what? This is pretty simple. It's the energy supplied, to the circuit. You can think of it as an electrical energy source. I'll put it in red. You can think of it as an electrical energy source. And vice versa, the other one is electrical sink. Electrical energy sink. Alright, so the answer for this is, so one answer for defining what PD is, and one answer for defining what EMF is. So those are your 2 points. Question number 12. On the diagram, mark a point where on the water surface whose motion is exactly 180 degrees out of phase. Now, to remember, the question shows that this is actually a wave on the surface of the water at one instant of time. The wave is traveling to the right, so that's also important, traveling to the right. Alright, so now what do we know? Mark a point on the water where it's 180 degrees out of phase. So let's zoom in. So we know that from here all the way to here is one wavelength, right? Or it's 360 degrees. 180 degrees out of phase must be half, so this is our 1 lambda. 180 should be lambda over 2, so half the wavelength, right? So we go to x, And first we need to find out what half of this is. So that is, you can see this is 1, 2, 3, 4. So four of these large squares, large partitions, you can see from the gray lines, right? So we go here, we go from X and we measure 4. So 1, 2, 3, and 4, and we go down to the point. So this is our point, and we label the point A. So that's our point A. Okay, now draw an arrow at point Y to show the direction in which the water is moving at the instant shown. So it must be perpendicular, right? Because it's a water wave, it is going this direction. So Y must be perpendicular. Now in this case, Y cannot be traveling up because the wave is traveling up. So that means Y must be traveling downwards. Okay, now we've done that. So that's our second point. Next we have what? Mark a point on the water that is at rest at the instant shown. Now what does rest mean? Rest means, in this case, means maximum displacement. Maximum displacement. Now in that case, what's that? So that will be over here, here, and here. Any one of them, if you label B, will get you the 1 mark. Alright, so that's question number 12. Now question number 13. What is coulomb in base units? So coulomb is the unit for Q. Now we need a formula in terms of Q. Q is IT, isn't it? Now what is I measured in? I is measured in A, which is measured and times by time, which is in seconds. So our coulomb should be the same thing as AS, right? Ampere second. Okay, so that is the answer. The answer is AS. Okay. The diagram shows the part of an electrical circuit. Determine the magnitudes of the current I1, I2, and I3. Now the easiest one is 30 milliamps to I3. It must be the same thing because it's after all of this is done. It's the same wire, so it must be 30 milliamps. That's the easy one. Now in a parallel circuit, we know that I is split up. The current is split up in parallel. So 30 milliamps should equal 20 milliamps plus I1. So I1 must be 10 milliamps because 30 take away 20 is 10. Okay, so we've done that. So we know this is 20, right? What else do we know? We know that this 20 meets this 15. This meets this 15, and then what? What else do we know? Meets this 15. But is this 15 relevant? Yes or no? Sorry, no. I knew it. Sorry, 10. So 10 meets this 15, and you're left with, over here, we should get 25 milliamps. And if this is 30, we need to work out what this is. So 25 plus I2 should equal 30. So I2 is 5 milliamps. It's very important that you remember the units. So that is the answer for I1, I2, and I3. Alright. Question number 14. A student looks at the sunlight reflected off of a puddle. She puts a polarizing or polaroid filter in front of her eye. As she rotates the filter, the puddle appears darker than lighter. Explain this observation. Okay, so tip for any and the tip for these types of questions where it require explanation is you need to state the obvious. State the obvious, and this will get you marks. This will guarantee get you marks if you state the obvious, because they want you to state the obvious. Okay, so what's the obvious here? the obvious here is that the reflected light is polarized. So that's the obvious point that you need to mention. So the reflected light is polarized. Next thing you have to do is explain what polarized means, and then we have to explain what a Polaroid filter does. Okay, so what is polarized light, right? So we know that a polarized light only travels in one plane. Only travels I'd say only vibrates, let's say vibrates or oscillates. Your oscillates is also fine, oscillates in one plane or one direction, one plane. Okay, so we have defined what polarized light is. Now we have to talk about the Polaroid filter. What does the Polaroid filter do? The Polaroid filter only allows so again, so I'll just use this vibration / oscillations, copy, paste, okay, and I'll make it partial. Oscillation vibrations in one plane to pass through. This is enough to get you the 3 marks. But you can also talk about that when, right? So we can talk about how when she rotates the filter, right? We can explain this when the puddle appears darker and then lighter. When does it appear dark? When both planes are perpendicular, right? When both planes are perpendicular. This is perpendicular. Lighter is when it's parallel. So parallel. Okay, so you can explain that. So you can say when the puddle appears darker, this is when both planes are perpendicular to one another. Both planes are perpendicular to one another. Perpendicular to one another. Okay, so the key marks are, so first thing is state the obvious. Reflected light is polarized. Second thing is to define what polarized light is. So I'll just write, so define this. Next thing, you also have to define what a Polaroid filter does. Then from here to here is you explaining the observation. From here to here is you explaining the observation. So you can easily lose marks if you don't state the obvious here. Obvious. Alright. So that is question number 14. Let's go to question number 15. The current I in a length of aluminium of cross-sectional area A is given by this formula. I equals NEVA. We also remember it as I equals NQVA. So don't get startled by why is it saying E instead of Q. It's the same thing. They tell you that E is the charge on the electron. Now, state the meanings of N and V. Now, these things you need to remember, because if you don't remember them, you will have to remember them. Okay, so N is the number of, so number of what? These are the charges, right? So this must be the number of charge carriers. That's it, charge carriers per, you also have to write per unit volume. Now, how can we get to this? Let's just make n the subject. So n would be I over QVA. That's how we know this is n, the number of charge carriers per unit volume. V times A will give us unit volume. Okay, V is just the average velocity. But of what? We can, just to clarify, it's usually the velocity of the charge carriers. Okay, show that the units on the left hand side of the equation are consistent with those on the right hand side. Okay, so this is pretty easy. So we can say the left hand side, the units are I, right? We know this, right? Now let's look at the right hand side. The right hand side, what do we have? We have N times Q times V times A. Now we know this is per unit volume, a number over unit volume. So that must be meter minus 3 unit volume times what? Times Q. Q is what? Charge. We know Q is IT from before, right? IT, and their base units are AS, right? We concluded that from before, from the previous question. So this is times by AS times by what's velocity is meters per second times by area is meters squared. So now let's bring it all together. We will get meters to the power minus 3 times meter of this times by the meter squared times by A times by S minus 1. So you can see that the meter cubed cancels out with the m and m squared, because you will get m cubed times m to the power minus 3, and they both cancel each other, and s to the power minus 1 cancel each other, so you're left with A for the right hand side. And over here I made a mistake here, this should be A as well, the unit, not the quantity, A. So the answer is it's consistent, so that's our 3 marks. So you get 1 mark for getting this, right? You get 1 mark for getting n, and you get 1 mark for getting to the end. Okay, so that is that. Question number 16. 2 lamps A and B are connected in series. They are connected in series with the battery. Lamp B glows more brightly than lamp A. Complete each of the following sentences, right? Complete each of the following sentences by choosing one of the phrases in the box. Now they have not told you to use all of the options. So it's very important that you remember that you do not have to use all of the phrases. So you don't have to use all of the phrases, because they don't tell you that. So don't be pressured in thinking I have to use all of them, because maybe you don't need to use all of them. Alright, so they tell you the current in lamp A is something equal to the current in lamp B. This is a series circuit, right? So the current must be equal. They're the same, equal. Now lamp B glows more brightly. Now what does that mean? That means this resistance is higher than this resistance. So I'll write RB is greater than RA. Now if I remember, V equals IR, right? So V of B, because I is constant, I times RB, and V of A is I times RA. So that means because RB is the resistance of lamp B is greater than the resistance of lamp A, we can conclude and say that the voltage of B, or the PD across B, is greater than the PD, or the potential difference, across lamp A. So that means it's greater than. So the answer here is lamp A is less than. Because this is talking about VA is less than VB less than. And because we know that the resistance of lamp A, we've already concluded that, right? RA is less than RB. So this is also less than. You can see here we have not used all of them. We've only used less than and equal to. We have not used greater than at all here. So it's not always necessary to use what you've been given. Okay, so same bulb, they're now connected in parallel with the battery. State which bulb will be brighter and explain your answer. So now, before I was constant, before I was constant, now V is constant, right? So we know nothing about I, but what we do know is the resistance. Resistance of lamp B is still greater than resistance of lamp A. We still know that from the previous question. Okay, so we need to get a formula that only requires R as the main thing that we're comparing, because V is still constant. So how do we determine which bulb is brighter? First we need to remember that the V is constant, so we can state, first of all, always remember, state the obvious. So we have to state that voltage, right? You can say that either voltage, or you can say resistors in parallel have the same potential difference across them, right? Always same potential. You can leave it that, but that is a key point. This is a marking point, stating the obvious. Okay, so next thing, we need to find a formula that will explain to us which bulb is brighter. The only formula that requires R and V is P equals V squared over R. Now, we know the V is constant, right? We know V is constant. So the only thing that will affect the lamps will be the resistance. So the power of A will be V squared over RA. And the power of B, why am I writing R? P of B is V squared over RB. Now we know that the resistance of lamp B is greater than resistance of lamp A. So that means that this is greater than this over here, the resistance here. That means the power A is going to be larger than power B. That means that bulb A will shine brighter. So bulb A will be brighter. So that's the end of this question. So question number 17. Two students demonstrate standing wave to the rest of the class using a rope. The diagram shows the appearance of a standing wave on the rope at one instant. Each part of the rope is at maximum displacement. Mark the position of one node, right? One node on the diagram. Label this point N. Now, this point N, so if I do a dotted line, maybe a straight dotted line. Okay, I do is dotted. So basically the nodes are at these points here where it touches the graph. I'm trying to make a straight line from the girl's hand to the guy's hand. So just one student's hand to the next. Okay, over here. Now the node is at this point and this point. So whichever point so if you label this N or this N, you'll get the 2 marks. You'll get the 1 mark. Okay. The arrow at X shows the direction in which the point X is about to move. Add arrows to the diagram to show in which points Y and Z are about to move. So over here, you can see the X is moving down whilst it's up, so Y must move up, right? Y must move up and Z must move down. So those are your 2 marks there. So Y going up and Z going down, that's your 2 marks over here. Now, the frequency of the vibration is shown in the diagram is 1.5 Hertz. When a rope is vibrating with its fundamental frequency, right, there is 1 antinode. 1 antinode means what? You have the graph itself, right? And then you have 1 antinode here. Now, which point is that? That is the point N. That is that point N over here. So that's 1. That's 1 node. So we have another node here. Then we have another node here. We have 3. So you can see there are 3 here. So calculating the fundamental frequency would just be 1.5 Hertz divided by 3. So our answer should be 0.5 Hertz. That's our final answer. And don't forget the unit. The units are very important. So 0.5 Hertz is our answer. Okay, so question number 18. Noise cancelling headphones were invented to cancel the noise in airplanes and helicopter cockpits. They work using the principle of superposition of waves. So sound waves enter and pass through the headphone and detected by a microphone, and then it produces an opposite wave. Compare the properties of the 2 sound waves that are necessary to produce complete cancellations. So the wave should be what? It should be the exact same wave but in antiphase, right? It must be out of phase. So it must be, the wave should be, it should counteract. So if I was to make it a bit smaller, so the wave should cancel out this wave, right? It should cancel out this wave over here. Right, this wave, right? So what's the property of this wave? This new sound wave we have, it must be what? The same size, right? Same amplitude. So same size. It must be what? Same size. Alright, same size. Must be same wavelength, right? You can see if it's not the same wavelength, then you will get something different. Same wavelength. What else? And it must be antiphase. Now, how do you convert that into words that we can answer the question? So we can say that it's, so comparing the 2 properties, we can say that is what? You have to say the 2 sound waves must have the same amplitude, which is to do with size, right? Use the terminology. Same amplitude and wavelength, as well as be 180 degrees out of phase, which is the same thing as saying antiphase. That is the properties. So let me just make this into mark, and so what are the 3 marks? So you have same amplitude is 1 mark, wavelength is another mark, and must be out of phase, or the same thing as antiphase, that's another mark. So those are your 3 marks for cancelling out the waves, right? Because if these two waves are out of phase and are of these properties, then you'll get a flat line which will cancel out. There will be noise cancelling. That's the whole point. Okay, part B. In practice, the incoming sound is reduced in volume rather than cancelled. Noise cancelling headphones work well when the noise is from a jet engine. Okay, they're not very effective at cancelling speech or music. Explain why. Now, the jet engine, what do you know about jet engine, right? Jet engine, we can say, jet engines, what? Sound, you can say sound, and the sound has what? It's very loud, right? It has a very constant pitch, right? It's very loud. It has a constant size or amplitude, constant pitch, or you can say amplitude or size, right? Now, because of that, you can see usually, so I'll just draw it here. So I'll write engine, like, just to explain. You have something like this, right? There is very constant for the jet engine, right? But for speech, right? Because we vary our speech, right? We can talk very fast and very loud, or we can talk very slowly. So what that means for speech, right? We can get something very different. It's hard to cancel out. So this is hard. So speech, this is much harder to cancel out. Much harder to cancel out. Because one wave cannot just cancel all of this. But in this case, you can see that if we have one wave, it can pretty much cancel out. It can pretty much cancel it all out. Cancel it all. But in this case, you can see that it will not cancel all of it out. You can see it won't cancel it out. It will be difficult. It will be difficult matching the signal. Difficult matching the pitch / signal. Let's say pitch. Okay, now because we know that now, so we can say it has a constant pitch. So what can we say about the jet engine? So it's easier. So it is easier to cancel the sound waves. And then you can say conversely, for speech, it is what? It's much more difficult to cancel the sound waves. Because what? Because the speeches, or you can say because the pitch is varied. The pitch, or you can say size, pitch / amplitude is varied. And that's why. So I've explained it through the diagram here, just so it's easy to understand. So we have the jet engine is pretty constant, right? Pretty constant sound, but speech is varied. So it's harder to cancel out with one single wave. So that's why it's not very effective at canceling speech or music. Okay, so what are the marking points for this? So for the marking points for this, we have to talk about that it's much more difficult to cancel out the waves, and because the pitch amplitude is varied, and for this it has constant pitch. So those are your 3 marking points. Okay, so now we are in question number 19. A 60-watt filament light bulb is used as a ceiling light. The bulb is 2.5 meters above the floor and is 5% efficient. Okay, that's pretty important. Calculate the visible light intensity on the floor directly below the bulb. Assume that distance r is spread over total area 4 pi r squared. So we need to remember the formula. I equals P over 4 pi r squared, right? So now what? So the power is only 5% efficient, so we have to do 60 times 5%. So that is 3 watts. So our power is 3 divided by 4 pi r squared, right? So 3 divided, so 4, and what's our r? R is 2.5. So 4 pi times 2.5 squared, and we get, let me check. So we get 3 over 4 pi times 2.5 squared. That gives us, so 0.038 or 19. It goes on, so 0.38, what's it, W, because that's watt, that's our watt, and that's meters squared, so W per meter squared. Meters squared. So you can round to 0.04, that's also fine, 0.04 W meters squared. Okay, meters to the power minus 2. Increasingly, a different type of light bulb is being used. It is a coiled fluorescent bulb. A 10 watt bulb could be used to replace the 60 watt filament bulb, and it gives the same visible light intensity. So that's important. So this 10 watt gives the same I. If it gives the same I, it must have the same P over 4 pi r squared, right? So it must have the same power. If it's having the same power, that means the 10 watt, from this 10 watt bulb, you're getting 3 watts of bulb that is efficient, right? So that means you're getting 3 over 10, so that is 30%. You get 30% efficiency, right? You get 30% efficiency. So that's pretty important. So approximately 25% of national power used for lighting. Discuss why some countries have announced that filament bulbs will be banned in the next few years. So the first thing we can clearly see that we have worked out is the fluorescent bulb. So the fluorescent bulb is, so the other one was 5% efficient. So we can say it's 6 times efficient, right? So 5 times 6 is 30. So is 6 times more efficient than the filament bulb. What else can we talk about? If it's more efficient, what does that mean? That means that you will have, this means that less than 25% of national power production will be used for lighting. Production will be used for lighting. What else can we talk about? We can talk about, so what else can we talk about? If it's more efficient, right? What's happening to the normal filament bulb? The filament bulb, usually what happens to it? It gets hot, right? Filament bulb, we waste energy through heat. The wasted energy is usually thermal, right? Which energy is thermal? Heat, right? So we can say less what? There is less, we can say less wasted energy as thermal energy. And that's it, right? Those are 3 points. So let's look at the mark. The marking scheme says, so having said this, right, efficient than the filament bulb, this is 2 marks because we use some calculations here, right? We use some calculations here, and this calculation is worth 1 mark. This is 1 mark, and the next 2 sentences are 2 marks. So if we talk about less than 25%, right, of the national power production, we get 1 mark. And if we talk about there's less wasted energy as thermal energy, that's our 4th mark if you wanted another mark. So this is 1 mark, and this is also another mark. Okay, question number 20. A sonic tape measures using ultrasound to measure distances in buildings. It sends out pulses of ultrasound towards a distant wall, records the time interval between a pulse being sent and its return. For one particular measurement, the time interval was 25 meters per second. So 25 milliseconds. Calculate the distance from the sonic tape measure to the wall. So we know that speed equals distance over time, right? we need to work out distance. Distance equals speed times time. But we also need to remember this time is for the pulse to go to the wall and to come back. So that means this 25 meters per second millisecond is measuring what? Is measuring 2 times the distance we want. 2 times the distance to the wall. So at the end we need to remember to divide by 2. This is at the end. Okay, so that will be 330 times 25. So 330 times 25. Why are we times by 25? It's millisecond, right? So also need to remember times 10 to the power of minus 3 times 10 to the power of minus 3 is 8.25. 8.25. So now we divide this by 2 because of this, right? Because of this, we divide it by 2. We will get, so divide by 2, we get 4.125. So 4.125 meters. Now in physics, we always need to remember to round. Now you can see here, they're rounding to 2 significant figures. You can see 2 significant figures. This is also 2 significant figures. So this, we also must round our answer to 2 significant figures. So that will be 4.1 meters. Right? Okay. Part B. Why is ultrasound transmitted in pulses? So why is usually ultrasound, in pulses? There must be a reason, right? The easiest reason we can think of is that there's no interference between the incoming pulse and the other pulse. So we can say there is no interference between the incoming pulse and the pulse being sent. That you can say that. You can also talk about that one pulse must return before the next one is sent. So you can also talk about that. So 4.1 meters. The answer for this is so that there's no interference between the incoming pulses and the pulse being sent. Okay. So question number 21. So an electronics student is using light emitting diodes to make traffic light. He uses red, orange, and green. The table gives the information about these LEDs. They are identified as 1, 2, and 3. Okay, so complete the table by filling in the color of light emitted by each LED. So I will remember it as Roy G. Biv, right? And I always remember this as having, so this is large wavelength goes to small. So that means that the largest wavelength should be red, right? So that this is the largest wavelength, this must be red. So Roy orange is next, so this must be orange. And we only have another color, which is green, right? So that's pretty simple. So that's why this is the answer. Calculate the energy of the lowest energy photon emitted by this traffic light model. Now, how can we calculate energy of photon? We can through the equation E equals HF. Now, to calculate the lowest one, we must have what? We must have the lowest frequency, right? In this, according to this, because H is a constant, this is a constant. So the lowest, so if I write E low, right? E low must be H and F low. So that means we are left with H. The constant is also given in the back of the exam booklet. That is 6.63 times 10 to the power of minus 34 multiplied by the frequency, which is 4.41. So that's the smallest frequency, right? Don't forget this, times by 10 to the power of 14. Don't forget that, times 10 to the power of 14. And we get what? We get, so if we put it here, so if we get 6.63 times 10 to the power minus 34 times 4.41 times 10 to the power 14, we get so you can see here they're all three significant figures. You can see over here, this is three significant figure. So whatever answer you get in calculator, you're going to round it to three significant figures. 2.92 times 10 to the power of minus 19. So the energy is, so this is obviously in joules, energy in joule. The answer is 2.92 times 10 to the power of minus 19 joules. Alright, so you get 1 mark for writing the formula down. That's pretty important, and 1 mark for the working out, and obviously 1 mark for the answer. Alright, question number 22. Okay, so a solar cell generates an EMF when certain wavelengths of light are incident on it. A student connects a solar cell in the following circuit. The student keeps the intensity in the wavelet constant, adjusts the variable resistor, and we get results. On the grid opposite, plot these results and draw a line of best fit. So if I just copy this, so let's go. First 4 points have been plotted for you, so let's go here and let's put it here so we know what we need to plot. Okay, so what has been plotted for us? You can see that over here, if you go 0.43 and 0.4, so this has been plotted for us. 0.5, 0.55, 0.6. So we have to plot the rest. So 0.3, this is 0.3, and we have to plot 0.46. So that is over here, 0.46, 0.2, 0.48. So 0.48 is here. And then what? Then you have 0.1, this is 0.1, go across 0.5, and 0.00 is 0.52. So this is this. So now we have to draw a line of best fit. Now the line of best fit should usually go across the whole point, right? It should go across 0 from the first point all the way to the last point, right? Which includes both of them. So in that case, I'm going to draw it in purple. It should go from here all the way here. And a line of best fit should be, I think in this case, should be like this. Should go across all. I think that's the line of best fit. Sorry. So that's our line of best fit. Let me change the color of that. Nope, never mind. Okay. Calculate the power output when it's 0.4 amps. So that's going to be, when you go across, you go up. So you go up here and go across. That is 0.43. Wait, no, actually not. 0.4 amps, sorry. 0.4 amps. 0.43. So that is 0.43. Okay, so we know P equals IV. So we know it's 0.4 amps times 0.43. So we get what? We times them, we get 0.172 watts. And again, we have how many significant figures? You see the most we have is 2 significant figures after the decimal points, or 2 decimal places. So our answer should equal 0.17 watts. Okay, that's that. Explain why the EMF of this cell is 0.52. Okay. Now, EMF is what? It's the electrical energy source, right? So we know that E equals V plus I and R. It's small r, right? We know that I is 0 when it's 0. When over here, if I highlight over here, so this is 0 all the way across. See over here, 0.52 here. When the current is 0, so when the current is 0, E equals V, right? And because E equals V, you get that the EMF is 0.52 volts. Okay, so calculate the internal resistance when the potential difference across the cell is 0.4 volts. So when it's 0.4 volts, you can see over here you have so around 0.5, 0.4, 0.4 volts is around 0.5. Okay, so we know that E equals V plus IR. We know that the EMF is 0.52. We know the voltage is 0.4. We know what else do we know? We know that the I is 0.5. Or now, how do I know it's 0.5? Go back to the graph and the information they give us. 0.4 volts equates to 0.5 amps, or terminal potential difference. So this must be, so we have to rearrange. That'll be 0.52, take away 0.4 equals 0.5 R. 0.5 R equals 0.12. So R equals 0.12 divided by 0.5. So we get 0.24 ohms. That is the internal resistance for this question. So this one over here, the answer is this. The answer for this is to show this is the equation, and because I is 0, we get E equals V. Okay, the 3 marks for here are, it's saying that obviously the answer, and we have to look at the lost volts, right? We have to work out the I and this equation here. Okay, the EMF of this particular cell is independent of light intensity. The current increases as the light intensity increases. Add to the grid above a line showing a set of results that might be obtained if the intensity of the incident has increased. So what should happen to the graph? So if you go back up here, let me draw it in another color. So if you go here, what should happen? It should be a similar shape to what we did here, right? But it should be above. Initially should be the I should be above, but at the end we should still get 0.52. So let's see over here, and we should still get the same endpoint, because we know the EMF is still 0.52. So that is the important part here. Okay, so that is that. Question number 23. So they give us a diagram that shows an experiment for the photoelectric effect. They tell you that the light is shone at cathode C, and a PD is applied between cathode and the anode A. So A and C here. A sensitive ammeter, so it's very sensitive ammeter, is used to detect any current. So they tell you that the light is replaced by one of the same intensity but a different photon energy. The result is shown below. So this is the results. They're asking us, so explain why the first ammeter reading is 0. The first ammeter reading over here is 0. Now, it's very important that we remember that if the photon energy is less than the work function, right? What happens then? If it's less than the work, or the photon energy is less than the work function, in this case it's of usually of lithium, as work function less than, right? What happens? This means that there isn't enough energy. For what? Enough energy for electrons to be emitted. Okay, so we have to first obviously understand we have to state that the photon energy is less than the work function. So that's the one mark. Second mark is to say that there isn't enough energy for the electrons to be emitted. Now, in the mark scheme, they also include, so if you were to include the definition of work function, you will also get another mark. So if, let's say, you did not write electron to be emitted, but you wrote the definition of work function, you would also get the mark. Okay, so So that's that. So part B, the experiment is repeated using the same two photon energies, but the intensities of the sources are increased. Add the new ammeter readings. So you can see that they have increased by a factor of 4, 1 over here and 1 over here, and now it's 4 and 4. So 0 times 4 is still 0, right? 0. But 5 times 4 times 10 to the power, so you put 4 times 5 times 10 to the power minus 12, you should get 2.0 times 10 to the power of minus 11. It's very important that you stay consistent with the decimal points. If it's 0.0, then you stick with 0.0. If it's 2.3, you stick with one decimal place. So you don't just write 5, or you don't just write 2 times 10 to the power minus 11, you write 2.0. It's a good habit to always remember that. Okay, let's move on. So we have, next question, we have CI. The cathode metal is lithium. Express the work function of lithium in joules. The work function is 2.3 electron volts. Now, this is also given in the back of your exam paper. I just brought this here so you remember. So 2.3 is, so 1 electron volt is 1.6 times 10 to the power of 19. So 2.3 will be 2.3 times 1.6 times 10 to the power of 19 joules. And we get what? We get 3.7 times 10 to the power of 19. Sorry, not 10 to the power of 9. Times 10 to the power of 19 joules. And it's important to remember to stay consistent with the degree of accuracy. The answer, obviously, it's not 3.7, it's 2.3 times 1.6 times 10 to the power of 19 is 3.68, which I have rounded 3.68. I have rounded to 3.7 to stay consistent with the significant figures here. So this should be 3.7 times 10 to the power of negative 19. That's the answer for this one. Okay. So what marks do you get? You get 1 mark for using this over here, and 1 mark for the answer. So ultraviolet radiation with photon energy of 4.8 times 10 to the power minus 18 joules is shown on to the lithium cathode. Calculate the maximum speed of the photoelectrons that are emitted. So we need to think of an equation, right, that has velocity and we can use photon energies. Now the only equation that we can use in this side in these scenarios is our HF equals our work function plus half mv squared, and v squared is obviously max, right? Okay, so now what? They tell us that the ultraviolet radiation is 4.8, right? So first let's work out what the kinetic energy will be, right? Kinetic energy. They tell us the work function is this much, right? They tell us the work function is this. So we know that it's, if you go back up, you can see that. All right. Okay. So over here, so how do you work out v squared? So first we have to work out the kinetic energy, right? So the kinetic energy will be, so this is the kinetic energy. If I just highlight it, this is the kinetic energy, right? So kinetic energy will be HF take away, so HF take away our work function. So that will be what? We already know what the photon energy is. It's 4.8, right? So 4.8 times 10 to the power of minus 8 take away. Now in our working out, we used the exact value. Now the exact value was what's 3.68. So we used 3.68. We don't use 3.7. We use 3.68 times 10 to the power of negative 19. Okay, so what's that? Let's see. So that is 4.8 times 10 to the power of minus 8. Take away 3.68 times 10 to the power of minus 19. That is, okay, wait, no, minus 18, sorry, not 8, minus 18, my bad. Minus 18. So that is 4.432 times 10 to the power minus 18. So that is what? That's kinetic energy. We know that it's half mv squared, right? Equals 4.432 times 10 to the power of negative 18. So v squared will be, it'll be 2 times 4.432 times 10 to the power of minus 18. And what's the mass? We know that the mass is, if you go down here, you can see the mass of an electron is 9.11 times 10 to the power of minus 31. So you go back here. So 9.11 times 10 to the power of minus 31. So our velocity will be, so you just square root that. So I'm just going to copy that. So I'll just square root this. Copy and paste. So our velocity should be, and then we will round it. So first we'll find what the answer is, then we'll round it. So that will be 2 times 4.432 times 10 to the power of minus 18. 9.11 times 10 to the power of minus 31. That gives us, this gives us 3.112 times 10 to the power of 6 meters per second. And then we round it to, you can see over here, this is two significant figures. So 3.1 times 10 to the power of 6 meters per second. So that is our answer here. So let me tell you what the working marks are. Obviously the answer is 1 mark. Half mv squared equals this is 1 mark. What else is another mark? Another mark is to use the equation itself. This is 1 mark. This equation here. And to calculate what this is. This is also 1 mark. So those are 4 marks. And that is the end of the video. I hope you guys enjoyed the paper walkthrough. And please share to as many people as you can that will benefit from this. And I'll see you in the next one.